Hey, welcome back. We're going to continue our conversation about continuity today by showing that a single function is both sequentially continuous and epsilon-delta continuous at every point. Now, this is an example of how we demonstrate sequential continuity, and it's also an example of how we demonstrate epsilon-delta continuity. I want you to understand as we go into this that this example is redundant because we will prove later that epsilon-delta continuity and sequential continuity are equivalent. But a good way to practice using the definitions is to do an example of proving that that definition applies. And so that's how we're going to get ourselves acquainted with these definitions. So let me remind you of the definitions here. F is sequentially continuous at a point x naught if whenever we have a sequence converging to x naught, then when we apply f to every term of the sequence, then we get a sequence converging to f of x naught. Basically, the limits of sequences commutes with the function f. We can move the f inside or outside the limit is another way of thinking about that. F is epsilon delta continuous if this condition applies. And we talked about that in the last video. So what we're going to do now is we're going to apply these conditions to a given example. We're going to use this function f of x equals x squared plus 1. This example could be, this process that I'll illustrate here could be modified to prove continuity of any polynomial function, but it would be a little bit of work. So let's get started here, and we'll see that one of these is surprisingly quite a bit easier than the other, and we'll talk about why in a few minutes. So let's prove first that this is sequentially continuous. So our first claim, and it's really just an illustration of how we use this notion of sequential continuity, is that f is sequentially continuous. And so where at x naught for every x naught. So in other words, we're just saying in an unqualified way that it is sequentially continuous. But since the proof will involve x naught, I'll just put the x naught in the claim there. So we're going to show that this function is sequentially continuous. So sequential continuity means whenever this limit of an is equal to the value x naught, then the limit of f of x an will be f of x naught. So we're going to assume that we have a sequence an and it converges to x naught. Let's see, we're going to prove this. So let an be a sequence, and we're going to assume about that sequence that its limit is x naught. And of course, that's as n goes to infinity. So we have a sequence and it converges to x naught. Now, what do we want to show? The goal here is to demonstrate that f of an is equal, well, that the limit of f of an is equal to f of x naught. So we need to calculate the limit of f of an. So the limit of f of an is the limit of an quantity squared plus 1. So here what I'm doing is I'm just applying the formula that we have for the function f to the term an. Plug in an for x in this formula, and we get an squared plus 1. Now, can we do anything with this limit? Well, absolutely, because this is a limit of a sum. And so we have a sum law for limits of sequences, and we can apply it here. This is the limit of an squared plus the limit of 1, where we think of 1 as a constant sequence. Now, I want to caution you here about uses of the sum law for limits. So let me remind you of the phrasing of the sum law for limits. So the sum law for limits says that the limit of an plus bn is equal to the limit of an plus the limit of bn, which is exactly what we've used here. And of course, these limits are as n goes to infinity. But of these three limits in the sum law for limits, any one of them, for a given example, could fail to exist. And so the sum law for limits also has to contend with the possibility that these limits would fail to exist. And it does so by saying, provided the right-hand side exists, which is really two provisos here. It is the condition that this limit of an must exist and also this limit of bn must exist. So whenever you use the sum law for limits in this way to dissolve a limit of a sum into two separate limits, then you're really proving this contingent on the existence of these limits. Now, we haven't justified, I mean, this one is obvious, but we haven't justified the existence of this. And so you may say, well, the sum law doesn't apply, or it doesn't apply yet. And that's sort of true. The sum law here is not yet justified. But if I continue this computation, And if in continuing this computation, I prove that this thing does exist, then after the fact, that justifies this use of the sum law for limits because the limit turned out to exist. So this is justified by the sum law for limits, which is really presumptive that this limit exists. If I continue the proof and prove that it does, then after the fact, that justifies the use of the sum law for limits. So let's continue here. This limit, so I'm going to think of an squared as an times an so that I can use the product law for limits here. Now, the product law for limits has exactly the same structure as the sum law, and it requires that both of the limits into which you break the limit must already exist. Do they? Well, in this case, yes, they do, and we don't need to worry about that because this limit is the limit of an, which we assumed up here was equal to x naught, and this limit is the same. So this is by the product law for limits, and we do have the justification for the product law because each of these is known to exist. And notice here that what we have really demonstrated here is that this limit actually does exist, which after the fact justifies the use of the sum law. So, these limits are known. This is x naught because the limit of an is assumed to be x naught. This other one is also x naught. And this is a limit of a constant sequence, which is 1. And so we can rewrite that x naught squared plus 1. Now, we shouldn't stop here. We should point out that this is the function f applied to the input f of x naught, to the input x naught. So that is f of x naught. Why should we point that out? Because that's what we're trying to show. We're trying to show that the limit of f of the sequence is equal to f at the limiting point x naught. And so this connects this limit to this f of x naught, which is exactly what we want to show. So we conclude, f of an is a sequence whose limit as n goes to infinity is equal to f of x naught. And that's as desired. So what have we shown? For any sequence an, which converges to x naught, then the sequence f of an converges to f of x naught, which is the definition of sequential continuity. And so we can conclude that f is sequentially continuous. Which is what was claimed here. So this is a demonstration that f is sequentially continuous. Now, next we're going to prove that the same function f is epsilon-delta continuous. And I remind you, on some technical level, this is redundant because we will later prove that epsilon-delta continuity and sequential continuity are logically equivalent. But it's supposed to be an illustration of what the definition means and how we use it. And so it still is useful. Let's claim that over here. So this is going to be our second claim. And we're going to claim that f is epsilon delta continuous at x naught for every x naught. Now, this proof is going to be substantially harder. I want you to look at this proof, and before I erase it, this proof was, I mean, not obvious, but also not particularly difficult. There was nothing really subtle or strange going on here. Basically, this proof relied upon the sum law for limits and the product law for limits. And these are laws for sequential limits that have been proven earlier in the course. The reason this was sort of easy, if you will, I mean, it's our first example, but this was not terribly hard. The reason this was relatively easy was that we already have quite a lot of machinery for managing limits of sequences. We have the sum law for limits of sequences. We have the product law. If you think back to how we proved those, it was a lot of work to prove those things. And so we've actually got a couple of significant power tools being brought to bear on this problem. And that's why this problem in and of itself is not particularly hard. Now, we don't have corresponding power tools for epsilon delta continuity. And because we don't, we won't be able to play some slick tricks like this, and this proof will be substantially harder. Now, when I say we don't have it, I mean that in this course we haven't proven it. And that's because the whole approach of this course is a sequential framework for thinking about limits and continuity. If we had a different framework, if we'd started with epsilon delta from the very beginning, then we could have power tools, and those power tools do exist, but we don't have them yet. And so we're going to sort of do this the hard way. Yeah, that's why this proof is going to be a little bit harder epsilon delta than it was this way. Okay, so let's have a look. The epsilon delta continuity is this statement here. It begins for every epsilon, there exists a delta. And so that should remind you of sequential continuity. For every epsilon, there exists a cap n. And we're going to take exactly the same attitude towards this proof. In order to prove that for every epsilon, there exists a delta, etc., what we're going to do is we're going to let epsilon be arbitrary, and we're going to choose delta immediately. But we won't yet know how to choose delta, and so we're going to leave a big blank space in the proof, and we're going to come back to that and fill that in. So, so that's exactly sort of analogous to what we did with sequences. So let's let epsilon be positive, and then I'm going to leave a large blank space, and I'm going to say choose delta. And I'm just going to put a question mark here because I don't know how to do that, and I'm going to fill that in later. And once I perform the rest of the proof, then we'll have a clue about how we need to choose delta. Now, after delta is chosen, it is clear what has to be done with x, right? We need to let x be arbitrary in the domain of f, right? That's the only way we're going to prove something about for every x in the domain of f. And then it's clear what we need to do with x. We need to assume that x minus x naught absolute is less than delta. Okay, and now it's clear that we need to address this inequality, and this is going to be the crux of it. We need to show that f of x minus f of x naught is less than epsilon. So, so then we're going to calculate that. So let's say then, so let's calculate f of x minus f of x naught, absolute value. And then a huge calculation will happen, and we're going to intend to end that computation with less than epsilon over here. And I don't know what will happen in between here and here, but starting this way helps me get into the right mindset. It helps me get into the mindset of I am going to compute this, and I'm going to show that it is less than epsilon. And if along the way I need to make some modifications, I need to like add a little one or something, add, change the terms a little bit, then I may, so long as they are still less than epsilon, and so long as all the inequalities, so I'm allowed equals, 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 I'm allowed less than or equal to, I'm allowed strictly less than, but I am certainly not allowed to use the wrong direction of inequality. So beginning this way and predicting how we're going to end helps me get into the mindset of, okay, I'm calculating, I'm allowed to let this term expand a little bit, but I'm not allowed to make it get smaller. And so that guides what we should expect to do with this term. All right, so what are we going to do? Well, we need to use the formula for f, obviously, right? We're trying to show that f here, I erased it here, but f is the function x squared plus 1. We're trying to show that the function f of x equals x squared plus 1. Let's put that over here. F of x equals x squared plus 1. We're trying to show that this function is epsilon delta continuous. So let's apply that formula for it. So this is going to be x squared plus 1, and this is going to be, sorry, that's minus. And this other term that is subtracted is going to be x naught squared plus 1. And so we get an immediate simplification because the 1's cancel, and we get x squared minus x naught squared. Now that's a difference of 2 squares, and so it should be natural here to expect that we'll get, let's put the minus first. We'll get x minus x naught times x plus x naught. And then we've got the whole thing in absolute value signs, but the absolute value of a product is the product of the absolute values. So let's just distribute the absolute to the product, and we'll get x plus x naught. Now, these are the terms that we need to get under control here. Now, so let's take stock. We know that x minus x naught is less than delta. And x minus x naught absolute value, right, appears right here. And so this thing is totally under control. That thing is less than delta. And it's strongly under control, right? I have the freedom here to backfill this proof and figure out what that thing, what delta needs to be so that this whole thing will get less than epsilon. So what I'm going to do now is I'm going to try to figure out what delta needs to be so that this thing will be less than epsilon. And I'm going to switch to the red marker, and the reason I'm doing this is because I'm going to begin making errors. Actually, I'm beginning to make one major thematic error, and then we're gonna erase and we're gonna backtrack so that you can see like, okay, what happened here and why is it wrong? So let's continue here. Now I'm gonna go to some scratch work and I'm gonna say, okay, x minus x naught times x plus x naught is supposed to be less than epsilon. And I know that x minus x naught is going to be less than delta. So what I can do is I can divide both sides by this quantity here. I'm going to get x minus x naught. So that's less than epsilon over x plus x naught. So what we've deduced here is that so long as x minus x naught is less than this quantity, then the product of these two will be less than epsilon. And so since I'm still pending a decision about what delta is supposed to be, then I can choose delta to be this quantity, right? This is how we usually do things. And so, so I'm going to choose delta to be epsilon over absolute x plus x naught. And that informs what we're doing here. So we're going to choose delta, and that's going to be delta is equal to epsilon over x plus x naught absolute. Now so if that is done, then we can continue this work here. This is, let's see, this is now going to be less than, so I'm just going to sub in delta for this. This is going to be less than epsilon over x plus x naught, right? That this thing is less than delta, and delta is equal to that quantity. So when I plug in that quantity, I get that less than inequality, and then I get x plus x naught, and then I get equals epsilon. So that's our scratch work here. But it worked, or at least it looks like it did. But I've written the whole thing in red, which is supposed to clue you in that something's wrong. So here, I would really, this is not, I mean, I see a lot of homework that looks this way. This is not obviously wrong. So what I would encourage you to do is just pause the video here and look at what happened and try to figure out for yourself why I wrote this all in red and why this is actually fundamentally wrong. So take a moment to yourself, figure out why this is wrong, and then come back to the video. All right, well, hopefully you've had a look and you might be feeling kind of mystified right now, or you might be feeling sure of yourself that you've figured it out. What's really wrong with this proof, and why did I write the whole thing in red? Well, half of it in red. What's wrong with this proof is the logical relationship between this choice and the way the proof continues. So let me point out the logical ordering of steps here. But before we do, let's look at what we were trying to prove. We're trying to prove that for any epsilon, there exists a delta such that for any x, then if this is true, then that is true. Now, epsilon has to be completely arbitrary in this proof. Delta must be proven to exist, and it can depend upon epsilon. X needs to be completely arbitrary, but is chosen after delta is chosen. And then this assumption it has to be assumed, and then this has to be proven. So the statement here has a certain natural logical ordering to it, and that ordering should predict the basic structure of the proof. Notice that it does, right? We're letting epsilon be completely arbitrary, and then we're providing a choice about delta, and delta is allowed to depend upon epsilon. And then having chosen delta, then we're letting x be arbitrary in the domain, and we're making an assumption, then we're trying to prove some conclusion, right? So superficially, the proof does model the basic logical structure of the statement that we're trying to prove, as it should. But there is a mismatch here. And what is it? The mismatch is that delta is chosen to depend upon x. Now, you might say, what's the difference? Depend on x naught, depend on x. Who cares? Well, we're trying to show that f is epsilon delta continuous at x naught. X naught is given in the very statement that we're trying to prove. It's a fixed constant value. X, however, is not even yet chosen. The symbol x at this moment does not refer to anything. The symbol x is introduced here later, only after delta is chosen. Delta cannot be chosen to depend upon x because x is introduced after delta is chosen. And it has to be because we're trying to say there is one single delta, not for every x a different delta, but one single delta so that for every x this will be true. And so the real error, so there's a terrible asymmetry between the x and the x naught here that should occupy a lot of your mind. And here I've treated them like they're the same kind of thing, but they're really fundamentally different things. X naught is a fixed constant value given in the claim itself. It's already given. X is not even yet quantified over, right? X is not even yet introduced in this proof. And so I would be just fine making epsilon depend upon x naught. That's not the problem. But I said epsilon, making delta depend upon x naught, that would be fine, no problem. But making delta depend upon x is no good. Cannot do that. And when I perform this scratch work, I basically force delta to depend upon x naught. And that means that this whole method doesn't work. And everything that I've written in red is wrong. So what are we going to do? Well, I mean, it's not so obvious. We need to make delta depend upon x naught, but not x. And in fact, there's no way to choose delta so that it doesn't depend upon x naught. This function, well, that's related to uniform continuity here. This function is not uniformly continuous, and so on its domain, which is the entire real line. So this function is like when I choose delta, it's possible to prove that I have to make delta depend upon x naught, but I'm not allowed to make it depend upon x. And so I need to do something slightly more clever so that I can make delta depend upon x naught, but not on x. So what are we going to do? Well, we're going to erase what's in red first because it's wrong. And then I'm going to try to modify this term x plus x naught here. That was the term that I kind of wanted to divide and say epsilon over that was going to predict the value of delta. That was the term I wanted to divide to both sides, and that failed miserably. And so I'm going to modify it. And what we're going to do is we're going to take the x term and we're going to write it as x minus x naught plus x naught. And then we'll have 2 plus x naughts here. So basically what I'm saying here is that x is about x naught, but the difference is x minus x naught. So basically all of this stuff is this single x here, right? I've opened that up to x minus x naught plus x naught. Now the reason for this, the reason this should occur to you, this might seem like sort of a magical step. The reason this should occur to you is because x is something we cannot let delta depend upon. X naught is something that we can. When we think about x as being close to x naught, then we like to think of x as being x naught plus a little bit of error, like x naught plus a little delta. It's pretty much x naught, but then there's a little extra something, some difference. So basically by writing x as x minus x naught plus x naught, what we're really doing is we're focusing our attention on the approximation x naught plus the error in that approximation x plus x naught. And this is a convenient way of doing that. Now, so now what? Now, obviously, so we're not going to cancel these x naughts because we get back where we were. We're going to combine these x naughts, and then we're going to have this error term. So this is going to be, I'll just copy this portion. This is going to be x minus x naught plus 2x naught. So that is certainly more complicated than what we had before. But notice the term x minus x naught is something that we can hope to have some control over. And so what we're going to do now is we're going to separate that term. So this is going to give us, so absolute x minus x naught times, and now we're going to split this with a triangle inequality. So that's going to be absolute x minus x naught, and then plus 2 absolute x naught. Okay, I pulled the 2 outside the absolute because it's a positive constant. So that's actually, I often make this mistake. That's triangle inequality, so I should have less than or equal to here. So that's by the triangle inequality. Notice I also have this other term here, which would affect the directionality of this triangle inequality if this term could be negative, but this has absolute value signs around it, so this is going to be non-negative, so we don't need to worry about that. All right, now we have some control over this term, and we have some control over this term. And you might be thinking that now I have something that I can divide by, right? I can divide. So I'm switching to red here. So you might be thinking, oh, now we will just begin our scratch work and we will say x minus x naught times that monstrosity is supposed to be less than epsilon, so I'll divide, well, let's see, less than, and then this is going to be epsilon over x minus x naught plus 2x naught, and I'll divide both sides by this ugly thing. And okay, yeah, I mean, this is correct algebra, but it's not correct logical thinking, because again, I will get, like, if I try to assign the value of delta to that, then again, I will get myself into a situation where delta depends upon x, which is the fundamental error that we had before. And so I'm still not in a position to divide by this. But you might think that here's another option, which is, well, I guess I should stay with red because it's not going to work. You might think that this is now more under control than this was because this is less than or equal to delta. And so I might say, okay, that's going to be less than or equal to x minus x naught times, here's a delta plus 2. And then I could divide by this. And okay, but if I do, then I'm going to get something like epsilon over delta plus 2 absolute x naught. Okay, so that's nice, but the problem is then I will try to assign this to be delta. And if delta can't depend upon x, then it certainly can't be chosen to depend upon the value of delta, right? I could, get myself into a lot of circular problems this way. And so I can't choose delta to depend upon delta, and so this won't work either. And so we seem kind of stuck here. We want to control this term. We feel like we can if we just divide by the rest of this nonsense, but the rest of this nonsense either depends on x or depends on delta. And so what on earth do we do? Well, it's not so obvious. We need some level of control on this term, which is independent from the level of control that we get on this term. And that might sound crazy because it's the same term, but let me show you what I mean. So I'm going to switch back to black because I'm hopefully not making a mistake here. So what we're going to do with this term is we're going to say, let's control this term so that that is less than or equal to 1. Okay? So basically, I'm going to bound x minus x naught by 1. And here, I need a justification for that. And I'm going to give the justification because x minus x naught is less than delta. But wait a minute, that's not a justification for saying that x minus x naught is less than 1, right? I mean, if we don't know the value of delta yet, then delta could be 2, and being less than 2 doesn't make it less than 1. Let's furthermore assert here that delta is going to be less than or equal to 1. Now, this might seem like, well, wait a minute, how do I know that delta is less than or equal to 1? This is a condition that I'm now committing to, and I will have to enforce upon myself when I choose delta, right? So basically I'm saying here, I can get this this is less than delta and therefore less than 1, provided that later I follow through and make sure that delta is less than or equal to 1. This is exactly analogous to the step in the epsilon n proofs where we said, okay, I can make this such and such weird change, provided that n is at least 7, right? When we said that, we were basically committing ourselves later to a choice of cap n where it was at least 7, so that that would be true, right? And we were able to pile on those additional constraints to the little n, so long as we were able to then backfill those constraints and keep all of those commitments when we made the right choice of cap n in those proofs. So basically what we're doing here is we're making a condition on what commitment we will later make about delta, and we will have to remember this condition, and we will have to stay consistent with this condition when we choose delta. Okay, so that's basically how we get this term under control, is we make a preliminary constraint about delta, which is that it's going to be less than or equal to 1. And that'll give us a less than or equal to here. Notice that everything else here is positive, so you won't have the sign switching because you've multiplied by a negative or anything. Now, the joy of doing this is there are actually 2 huge benefits to doing this. When we make this change, number one, this thing no longer depends upon x. And so all that argument, all that reason for switching to red because I was dividing by something that depends upon x, all the problem caused by this thing depending upon x is gone. It doesn't depend upon x. Well, this thing doesn't depend upon x anymore. So that's great. The other thing that we need to worry about is, and I didn't make a big deal about it before, when we divided by this term, we always risk are we or aren't we dividing by 0? And so it's always problematic if we're risking dividing by 0. It's not obvious whether this term could be 0, right? If x is equal to x naught and x naught is equal to 0, then in principle, this term could be 0. But this thing cannot be 0 because this is 1 and this is non-negative. And so we will be safe to divide by it. So finally here, I'm going to switch to some scratch work, and I'm going to say, and it's going to be fairly obvious. Let's bubble out some scratch work and distinguish it from the actual proof. I'm going to say this thing times 1 plus 2 absolute x naught is less than epsilon, and then I'm going to divide both sides by the obvious thing, and that's going to be epsilon over 1 plus 2 absolute x naught, and that was easy. And so I guess that's my choice of delta. So that tells me how I need to choose delta. Basically, just choose delta so that when you multiply delta by this thing, you'll get epsilon. So that's what we're going to do. That's what we're going to use for delta as we continue this proof. Now, therefore, and this will make you nervous, therefore, I'm going to choose delta to be epsilon over 1 plus 2 absolute x naught. So that's my choice of delta. And then now I already have here, so that actually preceded, notice it doesn't depend upon x, that preceded the choice of x, and it preceded the assumption that this x minus x naught is less than delta. But under that assumption, then this thing is less than delta. So this gives us less than, and then delta here, delta times 1 plus 2 absolute x naught. And then, of course, delta times 1 plus 2 absolute x naught is just epsilon. And then as desired. Yeah, okay. So that looks pretty good. So let me step back from this and you tell me, maybe pause the video if you want. You tell me if you see any errors in this. Well, you can't tell me, but do you see any errors? There is one, and if you're paying attention to my use of color, then you already see where it must be. It's here. So why is that an error? That's completely consistent with our scratch work, and it doesn't depend upon x. The only error that we still have here is, well, this thing. I made a prior commitment that delta is not allowed to be greater than 1. And then I said, okay, let's just choose delta to be epsilon over 1 plus 2 absolute x naught. Now, epsilon is completely arbitrary. X naught is completely arbitrary and unknown. I have a 1 here, but I don't have any reason to believe that this is less than or equal to 1, because I don't have any idea what epsilon is. And if not, then I don't have any justification for this step, which means the whole proof will collapse. So the only thing that I've done wrong here is I've used my scratch work to successfully choose the value of delta, but that scratch work is not necessarily consistent with my requirement that delta should be less than or equal to 1. And so I need to modify my choice of delta so that I am sure to keep the commitment here. Now, we've done something similar to this many, many times with our sequences. We have a commitment that n is supposed to be greater than 7, but another commitment that it's supposed to be greater than the square root of epsilon, or maybe 1 over the square root of epsilon or some crazy stuff. So if we have several commitments for what n is supposed to be greater than, then when it comes time to choose that cap n, we need to choose it so that little n will be greater than all of those things. Now here we have a commitment that delta is supposed to be like this, but we have another commitment that it's supposed to be like this. And what we're going to do is we're going to choose delta to be the minimum of these two values. And then if we look carefully at the proof, we'll see that that will work. So I'm going to erase this, and my scratch work is in my way a little bit, so I'm going to get rid of that. I'm going to erase that, and I'm going to say then delta is going to be the minimum of the value 1, which we meet, basically we're not allowing it to be greater than 1 by saying minimum of 1 and something, then it can't be more than 1. It's going to be the minimum of 1 and epsilon over 1 plus 2 absolute x naught. So when delta is chosen to be the min, then what do we know about delta? We know that delta is less than or equal to 1, and we know that delta is less than or equal to that. Now, that means that if we think of this as a substitution, this thing is less than delta, is that still true? Do we still know? Well, yes, that's still true because this is, but we don't know, we don't know that, so it becomes a little bit complicated here when we think about what happens to delta times this. So either delta is equal to epsilon over 2 plus absolute x naught, in which case they simply cancel and give us epsilon, or delta is equal to 1. But in that case, 1, the only way it would be 1 is if this was the larger of those values, in which case delta times that value would still be less than or equal to epsilon, right? So basically we're showing that delta is going to be less than or equal to 1 because it's minimum of 1 and something, and that's going to justify this line. Delta is going to be less than or equal to this value because it's the minimum of this value and something, and that's going to justify this inequality. And so both inequalities that we need are justified by this single choice of delta as the min. And notice furthermore that this minimum is a positive number. The definition of epsilon-delta continuity requires that there exists a delta and that delta be positive. Well, 1 is positive, epsilon is positive, and this is a positive number. And so that's definitely a positive number. And so this completes the proof that F is epsilon-delta continuous. So F is epsilon-delta continuous. Now, that was rather hard. That was our first definition. That was our first proof of epsilon-delta continuity. And I chose a quadratic instead of a linear function. And so it was a little bit of effort here. Direct proofs of epsilon-delta continuity like this are hard, and certainly much harder than the sequential continuity proof. The reason it was so much harder than the sequential continuity proof was because we didn't have any special power tools to apply to the problem. The right way to approach this long term is to say, what are the important abstract power tools that we need? What are the theorems about epsilon-delta continuity that we need in order to get this working? The most important theorem, though, I mean, you can build the theory using limit laws and statements about continuity, thinking about epsilons and deltas instead of thinking about epsilons and n's and sequences. But from our point of view, we already have the theory of sequences. And the simplest way for us to move forward is to simply prove that epsilon-delta continuity and sequential continuity are equivalent anyway. And so whenever we want the luxury of dealing with sequences, then we can think about sequential continuity. And whenever we want the luxury of thinking about epsilons and deltas, then we can use those. So that will make us into sort of an ambidextrous situation that we can use whatever we want whenever we want. In order to do that, we need to show the equivalence of these two definitions of continuity.